Hello everyone, my name is Dewi and I am a PhD candidate from Curtin University. I'm here to present my preliminary analysis of my research about educational affordances of three learning media, physical models, computer simulation, and immersive virtual reality in improving students' chemistry learning. This project is led by Dr. Mihai Won and funded by Australian Research Council under Discovery Scheme. Okay, so for this project, we use three learning media. First is magnetic physical model, which is a representation of water molecule. You can see the red is oxygen and white is hydrogen. This model has magnet to emulate how water interact with each other. Second is computer simulation. We use Odyssey. It has capabilities to show dynamic and colorful simulation of electron density and other properties of water molecules. The third one is immersive virtual reality. We design our own educational program to explore ice crystal. I will talk more about these three learning media later on. So today the aim of this research is to understand the affordances and limitation of each media for learning chemistry, specifically about molecular interaction and structure. And I'm interested in the application of these three learning media for first-year chemistry students. For learning molecular interaction and structure, we design a learning experience using Snowflakes as the context. So we pose this very big question, why snowflakes has that particular shape? To answer that, students have to start from the basic. The water molecule, H2O, with oxygen partially negative and hydrogen partially positive. Therefore, when two water molecules get close to each other, oxygen will attract hydrogen and create an interaction we call hydrogen bond. Then, when these water molecules are in optimal position, they will form a tetrahedral structure. At low temperature, these structures will grow to ice crystal that has hexagonal pattern. The hexagonal pattern in molecular level can be observed in macro level as the six-fold symmetry of snowflakes. So there you go. So I mentioned we have three models, three media. So students will come as pair and they have to work together to go through all three learning media. First, they will use a magnetic model to cover the basics before going to computer simulation and IVR. So you can see here each medium cover different learning goals, and some learning goals, especially the fundamental ones like hydrogen bonds, are covered multiple times. And the whole protocols involve pre-interview and post-interview. So in the pre-interview, we ask some questions to assess the prior knowledge before they go through the media. The activity involves media. And then in the post-interview, we ask, what did you learn? And the evaluation of the media itself. So their engagement, is it fun or anything? And the whole thing took about 2.5 hours. So today I will just present the preliminary analysis, and for this analysis I use qualitative method. The data I analyze are videos of the sessions of 18 pairs of students and their hand-drawn diagrams. To assess the learning outcome, I counted the frequency of discussion per topic for each medium. So you can see numbers from 0 to 36 in the later slide. And to unravel the affordances of each medium, I use immersive learning experience framework by Won et al. And this immersive learning experience was designed to assess how immersive VR is implemented for learning, but I adapted it to assess other media beside immersive VR, so including magnetic model and computer simulation. And in this framework, there are 4 immersion categories: narrative, sensory, actional, and social. And we will go through one by one in the results section. Okay, so for results section, I organize it in 3 section. First one, we go through the prior knowledge before we dive into three learning media, and we finalize it with summary. Okay, so here we have a picture of snowflakes. So to assess students' prior knowledge, we ask students to explain what caused the shape of snowflakes and ask them to draw interaction of water molecules at a low temperature. Here on the right side, I have an example of students' diagram. So they explain the interaction between two water molecules pretty well. Here I mark it in green as green, so concepts like electron density, attraction and repulsion between hydrogen and oxygen, and they represent the hydrogen bond between two of them pretty well. However, when it comes to more water molecules, they struggle in terms of their position in space. Here I show it as a yellowish color. So therefore, their discussion in larger scales that involves many water molecules and snowflakes were very limited. Here I show it as red. So bond energy and scales, they did not discuss it at all in this task. So with this, let's go to medium 1, magnetic physical models. So here, students use magnetic physical models. It's magnetic, so it has haptic feedback, which can afford learning goals related to attraction and repulsion and hydrogen bond. Because with it, students can attach, detach, and feel the force, and then try to make sense of the energy involved in hydrogen bond and breaking and forming the bond. So here on the left side are the learning goals that could be covered using these magnetic physical models. And what else? Alongside haptic, the models also provide 3D visualization. By creating different structure, student can understand optimal orientation and structure. So student can create tetrahedral structure, like here, rings, or even more complex structure. So by this, they learn this optimal angle and distance and tetrahedral learning objective. How about the social immersion? So this activity are mediated by a researcher who gave prompts. So each student handles their own model. The overall interactions are more individualistic. So the results show with this level of sensory, actional, and social immersion, students are able to discuss the key learning objective pretty well. As I mentioned, the overall interaction are more individualistic. However, when they collaborate, so some students collaborate better by sharing their models, and then therefore they can create more complex structures. So this collaboration allow more actions like shaking the molecules to test which structures are more optimum. Because of this, there's emerging concepts such as hexagon in isolates, which relate to the six-fold symmetry of snowflakes. We did not expect this to come with this media. And this chart also show that the increase of Unix action in x-axis results in not result related to the more topics discussed by the students. So there's a positive correlation there between actions and topics. And here, after they gone through the media, we ask students to revise their initial diagram. So for students' diagram after the activity, we can see the main change is related to the position and orientation of water molecule interaction. This was a result of their exploration, as they noted that the models show you what is possible and what's not. Next, we have computer simulation. So in this simulation, we have three main tasks. First, students explore electron density, shown in colors around 3D structures of water molecules. And we have a text instruction on the right side. We will not go in details what the text is involved, but the text is there. And then with this task, they can change the perspective and see how water molecule interact better and how the electron density change. The next task in this computer simulation involves a simulation of liquid um, water, and we can see the dynamics of hydrogen bonds, how they kept breaking and forming. And so finally, they have these graphs of optimal angle and distance in relation to energy. So what they can do here is to manipulate parameters by changing the angles and distance of two water molecules and see how by changing those angle and distance change the energy and strength of the hydrogen bond. So by doing this, they can learn about optimal angle and distance of two water molecules interacting with each other. And then let's take a look at the social immersion. So with this media, student student feels more comfortable because they are more familiar with this and familiar with the text instruction. And because of the setups, we have only one keyboard and one mouse. Students assume the pilot and co-pilot role. The pilot controls and the co-pilot was just like navigate and say something, hey, can you move the slider or anything. And with this level of sensory, actional, and social immersion, students are able to discuss the main learning objective intended for this media and stick to the narrative. So whatever the text instructions say, they do it. However, there are some cases that this is not the case. So when students are more comfortable with the controls, they deviate from the text instruction a bit and explore more, which result in emerging concepts similar to the magnetic models. So we can see here because the students created because the students add water molecules and able to create a tetrahedral. Um, the learning goals about tetrahedrals are emerge in this media. And this chart, similar to the magnetic models before, also show that more discussion as a result of a more unique action performed. So positive correlation still happen here in this media. And we also ask students to revisit their diagram again. And after this computer simulation, we can see the main change is related to the position and orientation of water molecules interaction. Some students here even take an effort to write the angles and distance precisely there. So this was a result of their exploration and the rich information that the computer simulation provided, as noted by one of student here, Evelyn. Okay, next we have immersive virtual reality. So in this immersive virtual reality or IVR, we have virtual space. So the students transported into this winter wonderland and they have more bigger and much more water molecules to play with, and they felt a little bit of haptic from the controllers they holding, some kind of vibrations there. And with this, they can create structures. So you can see here students try different angles and different positions for, to connect two clusters of water molecule before they can see, aha, the hexagons. And then they can also change perspective. So picking up the snowflakes and then try to match it with the pattern, the hexagonal pattern in ice lattice, like that. We discussed the sensory and actional immersion of immersive virtual reality. So next is the social immersion. What happened here? Let me remind you again that this program that we designed allowed two students to be in the same virtual space at the same time. So here I show you a screenshot of what one student see. She can see the other student's head here represented by a grayish floating head and pink hands. So they can see where their friends are and talk to each other. And here, the text and audio instruction are embedded in the program. So there are minimal external intervention. They became more focused on their tasks. And they're working on the stream structure. And they also getting different perspective because they're in there together, so they can bounce idea. Let's say, hey, can you turn this molecule around so I can see it better, or what do you think about this? So those kind of exchange are possible in this immersive virtual reality, and they're getting different perspective literally. So here I show Jared's view and Gabby's view. In Jared's view, this same ice lattice, one layer of ice, sorry, not ice lattice, one layer of ice, he can see the up and down of the structure or chair conformation of the structure. But in Gabby's view, she can see the hexagonal pattern there. So even though they're working on the same structure, but because of their position, they saw a different aspect of the structure. Therefore, the experience became more rich. And with this sensory, actional, and social immersion, students were able to discuss all the key learning objectives expected and have a comprehensive discussion. So how's the learning outcome after immersive virtual reality? Here I show the diagram of one of the students, Toby's diagram. So the main change are in hexagonal rings and the 3D orientation. So he even took effort to draw the top view and the side view because it's different. So the 3D elements are there, are captured by the students. What he said is like, it was so easy to see the structure from different angle, so different perspective. And the other students, also told me what he saw from his perspective, so different perspective literally. And this is other learning objective they covered. So summary. So for the summary, I will show you the frequency of discussion per topic for all three media. So you can see here models for magnetic physical models. They cover hydrogen bonds, optimal distance, tetrahedral very well, and simulation other aspect of the learning goals. And for IVR is more comprehensive, more these topics are covered. This is because students had narrative, sensory, actional, and social immersion. So all four categories covered in immersive virtual reality. And here in green are the concepts emerging. We did not expect students to discuss this in this particular medium, but they did because they do more, they explore more. So in models, magnetic models, for example, because they collaborate and they create more complex structure, they were able to discover about hexagons in ice lattice. And however, not many students discuss the concept of energy involved in breaking and forming the bonds here. Even though we cover it in the media, we don't know why yet. We need to investigate more on this aspect. So the implication is we need to consider aligning narrative, sensory, actional, and social immersion to better promote a comprehensive understanding. An immersive learning experience framework can be applied to investigate other media. As I show you, we use it to assess the magnetic physical models and computer simulation. And the limitation is this is still a preliminary analysis, so I need a way to measure students' learning because just counting the frequency of topics is not enough to know the depth of discussion. Here are some references, and thank you for your attention.